Out of time, so thank you very much.
Thank you.
Next speaker is, it's Dr. Battino, who is going to talk about the transition elements from type 1 supernova.
Just use this. Can I point anything? With the black one. No. Black no. Laser. Ah, the laser. Okay. Okay, thank you. Thanks for the guys for giving this nice opportunity. I'm Umberto Battino. These are my collaborators. I'm going to present my latest results on type 1A supernova progenitor modeling. So just to start with a little bit of introduction. There's not much type 1A in this edition. So why do we care, first of all, about type 1A supernova? So, well, in astrophysics and in physics in general, well, we do care because 2/3 of iron from a GC perspective comes from this explosion of type 1A supernova, thermonuclear disruption in wide open binary systems, and maybe also fraction of P nuclei comes from this. So iron, of course, is a key element in planetary magnetic formation, for example, so for the measures of life, not only for the GC, from GC perspective, but also also plays a central role in the synthesis of protein enzymes. So it's quite a unique set of features. Addition to the characteristics like curve, this explosion can be used as standardizable candles for cosmic distance measurement. And so just think about the Nobel Prize of Physics 2011, where for the evidence of accelerated expansion of universe. So despite of that, though, yet the nature of this explosion is still a matter of harsh debate, right? So just a little overview of what we're up to. So I like to classify the progenitors of type 1A in near Chandrasekhar mass event and sub-Chandrasekhar mass event. Each of these classes can be achieved in a single degenerate manner. So when you have only a single wide open binary system, or in a double degenerate fashion, okay? In the case of near Chandrasekhar explosion, basically, you can achieve this status also, of course, in a single degenerate way, where you have a single wide of accreting hydrogen-rich material from a less evolved companion. Although this channel, basically, if you by checking the expected amount of UV flux from the accretor and checking what you observe in early type galaxies, it looks like it cannot be contribute to more than a few percent, or 6% or something like that, of the total type 1A rate. But you can also achieve a near Chandrasekhar explosion in a double degenerate way. In that case, you have two wide ones with a mass ratio lower than 0.8, roughly less, so where the more massive wides will tightly disrupt the secondary, forming an accretion disk, and from there, starting a slow accretion. And if you do that, you do reach a Chandrasekhar condition, and although the final outcome really depends on the accretion rate and, of course, the wide mass ratio. Concerning then sub-Chandrasekhar mass event, in a single degenerate way, you can achieve this if the mass accreted from the less evolved companion is helium-rich. In this case, well, you trigger a double detonation on the surface of the secondary, which triggering the formation of waves that converge and then propagate to the center, igniting carbon in the center. And this looks really like could be really a major channel of the total 108. Estimates around 70% today suggest, although we still need at least a chunk of explosion coming from near Chandrasekhar mass event, around 30%. Otherwise, just assuming all the type 1A come from this channel, this will lead to an overproduction compared to iron elements like vanadium, chromium. To avoid that, you need it is a minor channel, not much, but 30% or something like that from near Chandrasekhar kind of explosion. In the end, of course, you can also get a sub-Chandrasekhar explosion in a double degenerate fashion through violent merger, especially when you have two wide of the roughly same mass. In this case, both are tidally disrupted. A violent merger will occur in sub-Chandra condition, or if you have at least around 10 to the minus 2 solar mass of helium, which will trigger explosion even during the merger phase. Okay, but so we still need about this much of neutron explosion on a GC ground, and if only a few percent can come from hydrogen accretion, then we will need, this means they will need something like maybe 20% or something like that, so a little bit coming from the low merge of type to white dwarf. So that's what I'm going to focus in this talk, in this work. So what you have here are my recent simulation of the progenitor phase of the slow merger to carbon-oxygen white dwarf. In this case, there are two basically white dwarf 0.9 solar massive initial mass. This keeping on diagram, you have the mass coordinate here, the center, the surface, and time as moves forward. You see the mass accretion here, and as mass starts to increase, here you have the temperature profile as a function of the temperature or the density. The surface is here, the center of white dwarf is here. This bump corresponds to the base of the accreting material. And you can use the total mass as a proxy of time. You start accretion where the primary white dwarf has a mass of about 1 solar mass. You have this profile here, bumping here. As the accretion goes on, the mass increases. You see the temperature at this peak keeps going up and up and up. As this peak is governed by the compression and heating of the material and the diffusion due to the generous electron towards the center. As you go forward until you exceed 1 gigakelvin at the base, so carbon burn ignites before it does in the center. So before it ignites in the center, driving the simmering phase. And if you do that, you trigger a carbon flash on the surface. In an HR diagram, you'll see these features similar to HB, but on the other way, because you don't have an envelope that expands and cools. And this carbon flash will drive this formation here of this convective region. The only difference is to model the accretion rate. Is an higher accretion rate, is a lower. If you zoom in this region here, you see the formation of this convective region on the surface, which then repeats them as the accretion goes on. And these are carbon flashes. And if this occurs all the time, the mass accretion rate exceeds 10⁻⁶ solar masses per year. And if you do that, you ignite carbon-12 on the surface, in particular carbon-12 emitting an alpha particle. And this alpha particle can be captured by the neutron-2, which comes from the previous IGB phase, and release neutrons via the alpha N reaction. So you have neutrons there, like a weak explosive of massive stars but on the surface of a white dwarf. And when this is happening, basically you start forming high transition elements on the surface. Here we have this movie shows the abundance in mass fraction of some key elements and the mass coordinate from the center to the surface. And you see as you trigger these flashes, you ignite it here, the from wave propagates for a while, and then you start doing these carbon flashes, go up, 2, 3, and so on. And you can produce pieces, especially first peak elements like krypton, zirconium. Not barium stays flat, you don't reach it, but you produce first peak elements to a production factor of an average times 1,000 times compared to solar or more. Okay. Of course, then the neutron-2 alpha is the main neutron source here. So what's the impact here? We did a little test. So here, in these plots, you see what's happening when you ignite a carbon flash. The temperature goes in excess of 1 gigakelvin. But then when the accretion goes on, you have repeated carbon flash. You see these dips in the carbon-12 abundance where carbon is consumed, and then the accretion goes on. You see there's a little step here. This is a krypton-6. This marks the formation in real time of krypton-6 by neutron captors right here. And if you, depending, I did a little test here, doing this calculation using the two most recent neutron-2 alpha reaction rate, one from Ardsley et al. 2021, the other most recent by Vischer et al. 2023. If you use one or another, especially if you use the Vischer et al. 23 rate, basically the production factor of krypton-6, rubidium-87, strontium-88, yttrium-89, zirconium-90 increase by a factor of 2.4. You see, and this is the same result you will get if you manually increase the neutron-2 alpha rate by the same factor. So there's a linear scaling of these abundances with that. And this basically provides a new scenario where this reaction really matters, and another motivation for the ongoing new direct measurement of this reaction at the Grand Sasso National Lab under the ERC standing grant of Shades on their best. Please also see there's two posters talking about this ongoing measurement by Danielle and Tom, poster number 143 and 84. Okay, so basically, this, after doing simulation, this is, now I'm not expecting you to see it, but I'll plot, you see a couple of plots showing this. You see, you obtain basically this distribution of elements up to the heavy elements. I produce basically 6 distribution for 6 models different by different physical input. In particular, we also get an increase iron 60 abundance by a factor of 20 more or less, compared to the case without the pre-supernova transitional enrichment. So basically, you take quite a significant amount of iron 60, and that if the type 1a explodes, the amount of iron 60 ejected is increased by 20 times, roughly. And this is also quite interesting, could be another signature of this kind of processes, and maybe a good case for next-generation gamma ray telescopes that will have the potential to detect single supernova remnants in the future. So what you can do then, you can take this basically, the results of this nucleosynthesis during the progenitor, and then can be used as initial abundance for the explosion, if they are put on the more external 0.1 solar masses. That's the buffer you enrich when you do this kind of simulation. And if you do that, we did a single lightweight explosion, since this paper is mostly focused on the progenitor. But if we try to run explosion using the model by Townsley et al. 2016, adding this pre-supernova self-consistently computed abundance on the external 0.1 solar mass layer. And if you do that, you get a significant amount of elements like gallium, selenium, but especially rubidium, krypton, and strontium, as you see here, all in excess of 10 to the minus 6 solar mass. And this is quite observable. It's quite interesting because this could, in theory, constitute a new observable smoking gun from a spectroscopic point of view, if this stuff can be seen, of a Chandrasekhar explosion, helping distinguish Chandrasekhar from sub-Chandrasekhar channels. And it's not that realistic since, 10 to minus 5 solar mass of strontium were detected in the kilonova of 2017. Here, we are not that far off from that limit, right? And so these are actually, and also most important, these are the distribution of the abundance I get from the slow merging of white dwarf or two white dwarfs, so this paper here, but also on the other channel from Chandrasekhar white dwarf forming from the single degenerate scenario, from the accretion of hydrogen matter. In 2020, you obtain something very similar. Also in that case, you obtain transitional elements all the way, in this case, to barium and also to lead, overproduced by a factor of 1,000. So it's a very similar scenario. And this means, independently of how you may form a Chandrasekhar white dwarf from a double degenerate or a single degenerate system, you are going to form transitional elements on top of that, which then will be ejected and possibly seen spectroscopically, okay? So summary and future perspective. So again, in this paper, as I was slowly merging wide dwarf approach to Chandrasekhar limit, basically, Camo-12 ignites on the surface before it does in the center, emitting alpha particles, which are recycled by neutrons and emit neutrons. And so neutron captures sets in, and formation of elements results. There's a large production of transitional elements, and in a buffer that, depending on the accretion rate, can vary in mass from the some 10 to the minus 2 to more than 0.1 solar masses. And this happens either way. So in the case of hydrogen-accreted white dwarf, and now we also know, also in the case of double degenerate system, especially krypton, rubidium, and strontium are produced by more than 1,000 times. And then, if you do it likely when you do explosion, gallium, germanium, selenium, krypton, rubidium, and strontium are ejected in high amounts and more than 10⁻⁶ solar masses. So the question is, can this be a new observable smoking gun of a Chandrasekhar explosion? Can we use this to distinguish sub-Chandra and Chandra? Because it's highly possible these elements can only be done in near Chandrasekhar condition. So can this be a new way to consider the progenitors? Of course, we need synthetic spectra from relativity transfer. This is ongoing work with Stuart Sim from Belfast. So can we see this? This is a key question. This is a great time for these questions. This great deep all sky surface is about to start. Think about LSST for most tides. And first and finally, iron 60 also needs to be noticed, increased by a factor of 20 when these pre-supernova elements are included in the initial condition of the explosion. So this paper has been also not going anymore again. It's not moving anymore. There you go. It's been submitted, just submitted, by 25 to ANA, so about to come. And that's all. The most important slide is the final, because that's it. Thank you.
Questions?
Thanks for a very nice talk. And I'm sorry if this is a very naive question, but my simple-minded understanding is that CO white dwarfs are just carbon and oxygen. So where did the seed nuclei come from?
No, there's nothing to do. So we have a metal. If you have, say, a solar metallicity star, right? All the carbon, neon, nitrogen, oxygen come in forming the metallicity. Basically, during hydrogen core, hydrogen burning will be converted to nitrogen-14. And then during the IGP phase, the nitrogen-14 will convert to neon-22, and it stays there. So it's present there from the IGP phase. So you have, on average, an amount of neon-22 or the same amount of the metallicity. And this is key. Yeah, so you need to use 22 in the simulation.
Umberto, thank you for the very nice talk. I have a question. So what is the sensitivity of the yields to the metallicity of the progenitors and the mass ratio? And also, why do you think that the galactic chemical evolution observations are not helpful, especially given the probably high sensitivity to the initial metallicity of the progenitors?
So why using the GC or and not the?
Are not useful, because you mentioned the direct light, the detectability in the light curves, but how about the abundances in low mass stars in the Milky Way?
Yeah, so GC, I will say that that's what you have right now. So there's no direct, I try to understand your question. There's no direct evidence of any progenitor so far, so you have all under evidence. That's what we have right now. So the GC I agree with you, is a dangerous constant, because depending on what element you feed, you can different answer. The number I quote there is the lowest fraction that you can get independent of what elements you feed. So it looks like you need that minimum amount of Chandrasekhar explosion. The other constant on the wider from the single generator comes from essentially from the expected. If you assume that single generator channel are maybe a prominent channel for type 1a, you observe a certain flux of UV radiation from the accretion system, which you don't really see. So that's the main thing. Why not using the abundance? Well, I'm not sure I get it right. How sensitive the yields? Okay. So the yields may essentially.
Don't start the discussion now. Just
okay, fine.
Short questions, long answers.
Okay. No, essentially that would impact the neutron-2 final abundance, because that's the main result. So the amount of neutrons, that's the main impact you get, and so that's the main impact we need to explore. Yeah, essentially.
Thank you. Sorry, I have also a question. In fact, if I have understood, the outcome strongly depends on the chemical composition of the outer layers.
Mm-hmm, yeah.
But because of the strong gravity, for instance, elements like iron 56 and neutralized elements, they go easily towards the central layers. So have you taken into account such effect, or do you plan to take into account this effect?
Well, the simile phase, in this model here, reaches 1.2. The inner 1.2. It depends how you treat. If you use Schwarzschild, Ledoux, Champion Sandy gets a lower amount of mixed material. But I still get, essentially hydrogen-rich material for the full 0.1 solar mass from 1.2 up to 1.37. So that is still there. It's not really mixed down. That stays there, fully mixed. What is fully mixed are the S-pros from the previous G phase. Those are fully mixed. But this newly made stays there in the rejector. Yeah.
Thanks.
Yes.
Next speaker is Dr. Casino, who's going to talk about the neutrino mass here. Oh, sorry.